This is example 3 when we are trying to diagonalize a matrix with repeated eigenvalues. In these particular examples, we see that it is possible to diagonalize A even though we have repeated eigenvalues. Alright, so let's remember how to do it. First, the matrix A must be a square matrix. In this case, it's a 3 by 3 matrix. And we're going to find D through the similarity transformation. We have to find P, the eigenvectors, and then we have to find D, the eigenvalues. To do that, the first step is to find the eigenvalues. Remember, we find the characteristic equations and we set the determinant of the characteristic equation to 0, and we solve for the eigenvalues through this factorization. In here, it is obvious that lambda equals to 1 is an eigenvalue. Lambda equals to minus 2 is also an eigenvalue. Because it's repeated, then we know that the eigenvalues are only 2, but the algebraic multiplicity for lambda equals to minus 2 is 2. So here is the detail. The geometric multiplicity is also minus 2, and we will also show it in the next few slides. Because this is so, therefore the matrix is diagonalizable. The other way to look at this is that lambda equals to 1, minus 2, minus 2 are all eigenvalues. There are 3 of them, although minus 2 is repeated. Okay, there are 3 of them precisely because matrix A is a n by n, 3 by 3 matrix. Now, to see whether the matrix is diagonalizable, now we have to find the eigenvectors, and we need to find 3 of them that are linearly independent. If we cannot find 3 of them, then the matrix P is not invertible. So this is actually the critical step for the diagonalization. Right, so remember how to find the eigenvector for the distinct eigenvalue of lambda equals to 1. That's simple, so we will not go through that. What about for lambda equals to minus 2? You'll realize that there are 2 free variables, and we can find 2 eigenvectors that are independent. When this happens, then we can count 1 eigenvector, 2 eigenvector, 3 eigenvectors that are independent. And because we can find it, therefore, we can now form P using V1, V2, and V3. And because they are all independent, P is invertible. Now, if you forgot how to find eigenvectors given eigenvalue, please refer to previous slides. The important thing now is that once we have formed P, we can continue, but let's have a sanity check first. We set A, we use EIG, the MATLAB command, to find P and D. We check that our eigenvalues are correct, which is 1 minus 2 minus 2. We find this is V1, this is V2, and this is V3, and we can compare it against them. So V1 is this one, V2 is our guess. And it's very hard to guess. What happened is that V2 and V3 should span the same space as this V2 and this V3. Should span the same space. Okay, so what you can do is you will see that linear combinations of these two is the same as linear combinations of these two. That's the idea. And for a check, you can see how I tried to do this verification using MATLAB. What I basically did was I find P2 and P3 and I extract them to form this matrix. I extract V2 here, minus 1, 1, 0, as a column vector, and I find the coordinates using this as the basis, and I realize that yes, I can find or I can generate V2 as some linear combination of this P2 and P23 matrix. So V2 estimate is exactly minus 1, 1, 0, which is this guy. Therefore, I can show you that V2 estimate can be formed by linear combination of second and third column of P using these weights, showing that actually they live on the same space. Okay, but this is a digression. This basically shows you how to map MATLAB solution to solutions provided by Lay for V2 and V3. Alright, finally, what do we do? Well, we have P, which is V1, V2, and V3. Now we can have D, which is lambda 1, lambda 2 repeated. And then we have P's and D's. And now we can check whether we did it correctly. We have the matrix A multiplied by P. So this is A and this is P. And we get equals to AP will be equals to PD. So we try it the other way around. We multiply P, which is what we have found. We have D, which is what we have found. And then we see that the matrices are the same. And therefore, we now know that D is the diagonal matrix, the similar matrix to A through this transformation. Alright. So in summary, this example shows us that even though A has repeated eigenvalues, which is minus 2 twice, this matrix is diagonalizable because for this lambda equals to minus 2, we can find 2 independent eigenvectors. We will now go to the next example, which is example 4, where we see that the matrix A has repeated eigenvalues, but it is not diagonalizable. So that's in the next video.